this video, we'll look at some more informational items. These are good functions to know, good properties to know. So the big definition here is that of continuous functions. And these are nice because you can envision these as being pretty safe functions to work with, because by their definition, these function types are continuous at every number in their domain. So these are not going to have weird discontinuities thrown at you. They're going to be fairly well behaved. And these types of functions are polynomials. Okay, so your cubics, your quadratics, things like that. Your rational functions. Okay, and now you might look at that and say, hey, but isn't a rational function discontinuous wherever the denominator equals 0? And yes, you're right. So rational functions can have discontinuities. All right, rational functions, you might get something like a graph that looks like this. They have vertical asymptotes frequently. Maybe you'd get something like that. But notice how the definition says these are continuous at every number in their domain. So that's the trick here. Every number in their domain. This value right here, where there is an infinite discontinuity, this is not in the domain of that function. So that's how the rational functions get away with saying, yes, we're continuous functions, continuous at every number in our domain, so please ignore this little discontinuity because it's not in the domain. Ha ha ha. Rational functions are very sassy today, apparently. So that is how we look at continuity on rational functions. Because see, for the bits that are in the domain, this portion and this portion, we do have continuity. There's nothing weird going on with those. The discontinuity is just at a value that's not in the domain. Okay, now root functions. Those may also have some places where they're undefined, like for example, taking the square root of a negative number. But again, that part, those values, negative values, would not be in the domain of that function. So they kind of get away with it. And the trig functions. Okay, so for sine and cosine, you might be able to envision that pretty clearly. Like, oh, those are nice continuous curves all the way. For the other functions like tangent, for instance, it has a lot of vertical asymptotes, but same thing again. The places where those vertical asymptotes are, those infinite discontinuities, those are not in the domain of tangent. So these are continuous at every number in their domain. Continuous functions. All right. Now for a theorem to go along with this, if you know the functions f and g are continuous, at least at a point, x equals a, then the following functions are also continuous at x equals a. So these follow the same type of principles as our limit laws. If you have two continuous functions and you add them together, the result will also be continuous at that certain point. Same thing if you subtract the functions, if you multiply the functions, if you divide the functions, well, as long as that denominator doesn't encounter anything weird. This is as long as g of a does not equal 0, so that f over g is defined. Okay, we don't want anything undefined. That wouldn't be continuous. So f over g, as long as the denominator doesn't equal 0 at that point a, okay. A constant multiple of any of those functions, okay, so like k, where k is a constant. K is a constant, no question about that. Okay, so constant times the continuous function f would still be continuous. And f to the n power, where n is a positive integer, so raising your function to some power there. N is a positive integer. Again, these are like what we saw with the limit laws back in 2.2. And then the nth root of a function, where n is a positive integer again. Okay, so this allows you to determine a wider range of functions that are also continuous at this point if you just know the basics about one or two smaller functions. If you know they're continuous, you can get all the rest of these from that.